Hi everyone, today I'd like to introduce logarithms and let's get started with a warm-up first. So we're going to warm up with two transformations. And so the first transformation is f of x equals -4 to the x plus 2 power. And I would always start with the parent function, which basically is f of x or y is equal to 4 to the x power. I would always try to plot points. We know this is exponential because the x is in the power. So in plotting points for x and y, I would always try to plot 0 and 1. And when doing that, when you plot 0 and you plug in 4 to the 0 power, that's 1. And when you plug in 1, so you have 4 to the 1 power, you get 4. So we're going to start off with these 2 points. We have 0, 1 and 1, 4. We know it's exponential. It's going to have an asymptote right here at y is equal to 0. And our graph is going to come along. Oops, missed the point there. It's going to come along and it's going to go up like that, exponentially. Now, what happens here is you're going to want to do your reflections first. The negative sign in front of the variable is going to be a reflection across the x-axis, whereas if you have a negative sign in the exponential, that's going to be a reflection across the y-axis. So with the negative sign here, we're going to reflect that. And basically what that means is this point right here, which is 0, 1, and this point here, which is 1, 4, when you reflect that, or basically reflect across the x-axis, or y equals 0, this right here is going to be 0, -1, and this point will be 1, -4, so 1, -4. And basically what that does is generally the equation is to take x comma -y is your reflection across the x-axis. Anyway, so far all we've done is take the reflection across the x-axis. This value right here, x plus 2, is actually going to move our equation that we have here 2 points to the left for our final destination here. So that's going to be -2, 0, and excuse me, that'll be -2, -1, and this one, if I move over 2 places, will be -1, -4, and my graph will end up looking like this. For this problem right here, a 1/4, so this one right here is actually, it is exponential, but instead of a growth, as this one started out to be on the left, because it's a fraction here, that's actually a decay. So instead of it going up, it's actually coming down that way, like that. So let's plot our 2 points. So we're going to start off with the parent graph of 1/4 to the x power, and I'm going to plot 2 points. The 2 points that I'm going to plot are 0 and 1 for x, and so 0 and 1. So we plug in 1/4 to the 0 power is 1. And when I plug in 1, I get 1/4 to the 1 power is 1/4. So 0, 1, and over 1, 1/4. So far our graph does look like this. Again, we do have our y equals 0 horizontal asymptote. Okay, there's no vertical asymptotes on an exponential equation, only your horizontal asymptotes. So this value right here reflects the graph across the y-axis. So now my point, instead of it being 0, or it's still 0, 1, but my second point, instead of it being 1, 1/4, will be -1, 1/4. And so now my graph, my second graph actually does this. This plus 6 right here takes my graph and moves it up 6 units. So instead of this being y equals 0, I now have an asymptote at y equals 6, and my graph will cross at 0, 1 from that. So that's going to be 0, 7, and this value here, which will be -1, 1/4, will be -1, 6 and 1/4. So that's going to be like that. Or 6 and 1/4. Okay, so that's our final graph. So we're going to start our introduction to logarithms, and logarithms are a type of exponent. they're the inverse of the exponent. So basically, the logs are inverses. And what that means is if we start off with an equation such as sec 2x plus 3, let's say, equals 5. The act of moving the 3 over, when you're trying to solve for x, your first step would be to subtract 3. Well, this is an inverse operation of plus 3 minus 3 is an inverse operation. So now I have 2x equals 2. In addition to that, dividing by 2 or multiplying by 1/2 is another inverse operation. So what you end up doing is an inverse of addition is subtraction, of multiplication is division, just like the inverse of logarithms are exponents and the inverse of exponents are logarithms. And there are the different types of logarithms. There are natural logs and our logarithms, base 10 and other bases. So here's a little background on logarithms. Basically, we usually talk about logarithms as just log, but and when we talk about a log, we also understand that a log is base 10. In the United States, our base is 10. We have 10 digits, 0 through 9. Different countries, different places have different bases because they have a different numerical system. So ours is based on base 10, and that's what we do. The logarithm is the inverse operation to exponentiation. That means that the logarithm of a number is the exponent to which another fixed value, the base, must be raised to produce that number. There's a couple of things that we're going to just practice with these two examples right here. This is log of 10. Now, if you don't see a value here where the base is supposed to be, that value right there is always going to be 10. And the reason is because our system, our calculators, everything we have is based on base 10. So if there's no base, it's base 10. If there is a base, if you do see a number below here, that value right there is the base. But in this case, that would be base 3. If I just wrote the value like this of log, just log of, let's say, x, and this would be base 10. Okay, x in this case, or the value that's right here, is our argument. We call it an argument. Okay, and you're usually going to set that equal to an answer, and let's just call that 2. So in order to solve this problem, what you would actually do is you would go base, and usually to base, you'd take base to across this equal sign is equal to the argument. So base, the 3, so I would say 3 to across the equal sign to the second power is equal to x. So in this problem right here that I just made up, 3 squared is 9. So x is equal to 9. In this problem right here, where it just says log base 10 of 10 is equal to, we don't know, so we're going to say x, you would go base to across the equal sign. So you'd say 10 to the x power is equal to the argument, which is 10. Now, if you have the same base here and here, and of course your equal sign in between, if the bases are the same, you can set your exponents equal to each other. So the answer to this problem is 1. Now, there are some little tricks that you're going to see as we go through. And one of them is when you have a log base anything to the same argument, that value is always going to be 1. Okay. If I had log base b of b, that's going to be 1. Any base, when these two values here are the same, you're always going to get 1. And the reason is you would go, again, like I had said just a few minutes ago, base to across the equal sign. So b to the 1 power is equal to b. And of course, that's the 1 power. If the bases are the same, the exponents are going to be the same. Let's do this problem right here that I missed so far. That's 10 down here. Again, we don't know what this is equal to, so I'm going to say it's equal to x. So I'd go 10 base across the equal sign. So 10 to the x power is equal to 100. Now, you can't set the exponents equal to each other here because my bases are not the same. However, that being a 1, I can make the bases the same. I can say 10 to the x power is equal to 10 to the second power. And now that my bases are the same, I can set my exponents equal to each other, and I have x equals 2. So John Napier, he discovered logarithms, and there's a lot of really cool research on him, and I would encourage you to read up on that because it's always an interesting reading about famous mathematicians. So I enjoy that. So a couple of things, converting between exponents and logs and evaluating logs. So that's what we're going to start with now. If you have y equals 2 to the x power, now we just finished a section where we were talking about how to find an inverse. Basically, one way to find an inverse is to switch your x and y. So I think we did a question maybe like 2x plus 3 equals 5. And so in order to, and I'm not finding the inverse if I don't have a y there. And in order to find the inverse of this function right here, which is, it is a line, you're going to do a couple of steps. Number one, you're going to switch your x and y. So then we would actually have 2y plus 3 is equal to x. So that's step one, switch your x and y. Step two would be to solve for y. So if I solve for y, I would get 2y is equal to x minus 3. And then I would divide by 2. So I'd have y is equal to x minus 3 divided by 2. And so that right there is my inverse. And in the previous slides that I went over, we talked about inverses and how we talked about inverses and that our domain and range for the original equation, let's say this one right here, my domain and range is reciprocated here for my inverse. So they're opposites. So in this case right here, that's how I find my inverse. But remember what I said about a logarithm is the inverse of an exponential function. So when I find the inverse here, of course, I'm going to switch my x and my y. So I have x equals 2 to the y power. However, how do I solve for y if y is my exponent? It's up there. How do I get it out of that exponential place? Now, if I just ask for the inverse, well, of course, I can just switch my x and y. But I haven't solved for y. So in order to solve for y, I would have to do its inverse. Like in order to take this exponent out of the exponential power, I would have to pull it forward. And in pulling it forward, what ends up happening is I'm taking the log of both sides. So I'm taking the log of that because remember, the inverse of a log is an exponent, and the inverse of an exponent is a log. Now, this being an equation, whatever I do to one side, I have to complete to the other side. So when I bring this y forward, I'm actually going to get y log 2 is equal to log x. And what then I would do is I would divide by this as a quantity. See that log 2? That's a quantity. And I would get y is equal to log of x divided by log of 2. And that would actually be my inverse. Now, there's, of course, another way to write this, and we're going to discover that a little bit later on in the slides. What you see right here is in this equation is x equals a to the y power. If I wanted to solve and find the inverse, of course, I would get y is equal to a to the x power. Now, again, remember what I had just said before on the previous slide. You take the base and go across the equal sign to the answer. So you would have a to the y power is equal to the argument, which is x, base to across the equal sign. Now, if I wanted to solve this, of course, I would then, if I wanted to solve this, I would pull this forward. Okay, but that they're not asking that. They're just saying, are these inverses of each other? Absolutely. You switch your x and your y. And then, of course, you're going to solve for y at some point. So we're going to practice that, converting between exponential and log equations. So what I'm looking for is this value. I'm trying to find x. I'm trying to solve for x most of the time. Sometimes if I don't see an x, like here, I'm going to plug in an x here. There's an x. In this problem right here, that is base 10, but there's no x. So in this problem, I can't even add an x. They're not asking me to solve. They're asking me to verify. So just in this problem right here, I'm just going to verify. So let's get started. We're going to go base to across the equal sign. So we're going to say 2 to the x power is equal to 16. So remember, in order to solve this, we're going to try to get the bases the same. So we have 2 to the x power. So 2 to the x power is equal to 16, which is the same thing as saying 2 to the 4th power. Now, if my bases are the same, I can set my exponents equal to each other, and x does equal 4. For this problem, we're going to go base to across the equal sign. So we have 10 to the negative 3rd power is equal to 0.001. Now, obviously, my bases don't look the same, so I'm going to attempt to try to get them the same to verify that these two values are the same on both sides of the equal sign. So 0.001 is actually 10 hundredths thousand, so that's 1 over 1,000. Now, another way of writing 1 over 1,000 is 1 over 10 to the 3rd power. Well, 10 to the 3rd power, if I actually move, this is a 3. If I brought this up, remember, I brought my denominator from the denominator to the numerator, that changes the power. See that 10 to the 3rd power? That will change that. So actually, this problem is going to be 10 to the negative 3rd power does equal 10 to the negative 3rd power. So this would be yes, that does verify. For this problem right here, we're going to go again, base to across the equal sign. So 6 to the x power is equal to my argument, which is this value right here. And remember, if you don't see an exponent there, you know that these are always 1. I mean, most people, when they're thinking of the number 6, don't think of the exponent 1 being there, or the value being in front as a 1, or it being divided by 1. Most people don't normally think like that, but you ought to know, even if you don't think that way, that there are these 1s all over the place like that. Bases are the same. I can set my exponents equal to each other, and then we're done. For this problem, we have base to across the equal sign. So we have 3 to the x power is equal to 1. Now, in this problem, what would x be? How would you, what to the 3 to the what power would equal 1? Well, in this case, 3 to the 0 power would actually equal 1. Anything to the 0 power equals 1. So in this case, x does equal 0. Now, there would be another way to solve this. So I do actually want to talk about that because, and I'm just going to make some notes down here. See this first problem that we did, and we said log base 2 of 16 is equal to x. And then we went 2 to the x power equals 16. Now, notice where my variable is. See that right there? My variable is in the exponential power. That's where it is. It's the exponent. And when your variable is your exponent, what that means is you have a choice of either trying to get the bases equal to the same, like we did up in the example, we did that. Or another thing that you can do is actually try to log both sides. And again, and this only works, you can only log when you have a variable as your exponent. And so what you're going to do is you're going to take this variable, which is x, and you're going to bring it out front. And I'm going to log both sides. So I'm going to go x log 2. And remember, because I do something to one side, just like an equation, if you were going to add 3 to both sides, you would have to do it to the other side. So if I log the left side, I do need to log the right side because it is an equation. And of course, x is equal to log 16 divided by log 2. Now, there's a couple of things I want to talk about right here. Number one, you never ever divide the logarithm, the logs. You can't ever divide that. Don't do that. That's completely wrong. This is actually a quantity, okay? And you can't break into that quantity. And what that does mean is that you also cannot divide the 16 and the 2. Excuse me for 1 minute. So you can't divide the 16 and the 2. So what you would do, this is what becomes a calculator problem. Remember, of course, you can solve it like we did up here. If you can get the same bases, then of course you can solve it. But I'm just showing you an alternate way. And so you would actually pick up your calculator, okay, and you would type in log 16. So you go log 16 divided by log 2. And personally, I would familiarize yourself with the calculator because you do need to know how to use the calculator, especially on the SATs, the ACTs, etc. And this one being my favorite calculator, this is the TI Inspire CAS. And so I don't know if you can see that, but this is the best one that I would buy for my kids. If I had the money. That is actually $145 or so. So they are kind of pricey. Anyway, when you go log of 60 or log base 10 of 6, and that was another thing here. Do you see that? There's no value here. There's no value in this area right here where there's actually a 10. So there's a little 10 there that we don't see, but we know it's there because it is base 10. See, so we actually went from a base 2 to a base 10. Okay, and that's how we did that. Anyway, when we get the answer, of course, is going to be the same as what we did. I believe we got a 4, so x is equal to 4. So likewise, the reason I brought that up right now is because of this problem up above that I just finished. Log base 3 of 1 is equal to x. So let's just do that problem one more time. Log base 3 of 1 is equal to x. So you would have base to across the equal sign. So 3 to the x power is equal to 1. Now, if you didn't know, because remember, you can only set the exponents to each other, equal to each other, if the bases are the same. And in this case, the bases are not the same, and they're never going to be the same. So I could, if I didn't know that x was 0, what I could do is I could pull this forward. And because remember, if your variable is an exponent, like this is, there's your exponent. And if your variable is an exponent, then you can log that to get that out. Because remember, an exponential equation is a logarithm. So that's going to go forward. So you're going to have x log 3 is equal to log 1. And you would get x is equal to log 1 divided by log 3. And again, there's a couple of things that you're going to get used to. One of the things that I mentioned before was, remember, if anytime you have like the same value here, that base is the same as the argument, that's going to equal 1. Well, anytime you have log base 10 of 1, that's going to be 0. And what ends up happening here is we have 0 divided by whatever log 3 is, and 0 divided by anything is 0. And so you would have x is equal to 0. And this is just done a different way. Your calculator will do that for you when you divide log base 10 of 1 divided by log base 10 of 3. All right, to finish this page, let's just finish. We are going to go base to across the equal sign. So 4 to the x power is equal to negative 16. Well, this actually is not going to happen because you cannot have a negative, you're going to have an undefined solution. You can't have a negative argument. Okay. Similarly, in this problem, so both of these two problems are kind of a trick problem. 2 to the x power is equal to 0. When are you ever going to get what power of x would you get to make that 0? And so there's actually no power that x could be to make that 0. So this is also undefined. You can, of course, bring that forward and go x log 2 equals log 0, and then go log of 0 divided by log of 2, and you'll still get an undefined solution. For this problem right here, we're going to go base to across the equal sign. So we have b to the x power is equal to b to the third power. Well, if your bases are the same, again, your exponents can be set equal to each other. So I do have x equals 3. Now, this problem is another one of those little tricks that logarithms have. And when you're base here and you have log base here too, 2 is my base, log base 2 of 9 is my exponent. When those values are the same, what ends up happening is I do get x is equal to 9. And so I know sometimes it's hard to just accept something like that. So I'm going to show you, I'm going to prove to you how this works. So in this case, let's just look at this one problem. So we have 2 to the log base 2 of 9. If I were to just take this on the side and go, well, what does that equal? Okay, so I'm going to go over to the side and go, well, what does log base 2 of 9 equal? So let's go, I don't know. 2 to the x power equals 9. Obviously, I'm not going to get the same bases, so I can't set my exponents equal to each other. So I'm going to pull that x out front. So I have x log 2 is equal to log 9. And I'm going to get x equals log 9 divided by log 2. So I'd like you to take a moment and actually do that. What is log 9? It's, of course, log base 10 of 9 divided by log base 10 of 2. So I'm going to go find the log button. So I'm going to go log base 10. And most people don't have to put the base in the calculator because it is actually, it is already in base 10. So that divided by log base 10. So log base 10 of 2. And that's going to be about 3 I don't know, what does that say? 17. So this value right here, this little x, is approximately, let me roll this up. Oh, can't do that. This value is about 3.17. So that's about 3.17. And so what that means is, coming back up to the top here, what we just found was this value right here, okay? We just found that. So if I went and plugged in what my x is, because that's my log base 2 of 9, and I said 2 to the 3.17 power on my calculator, 2 to the answer, or 3.17 power, you should get right around 9, or right, you should get 9. Your decimals, depending on how much you rounded off, your decimal might be like 8.998 or something like that. So anyway, but that's actually how I got this answer to be 9. So just to reiterate that, if I had, let's say, 3 to the log base 3 of 7, my answer would be 7. If I had 5 to the log base 5 of, let's say, 100, my answer would be 100. Okay? So this value here is just asking you log base 2 of 8 equals what? And so we don't know what that equals. So we're going to figure that out. I'm going to show you how to do this 2 different ways. So the first way, again, base to across the equal sign. So 2 to the x power is equal to the argument, which is 8. There's my argument. So what ends up happening is you're going to take 8 and break that down. That's 2 times 4. 4 breaks down to 2 times 2. So 8 is actually 2 to the 3rd power. And you're setting that equal to 2 to the x power. So you have x is equal to 3. Okay, and that's your answer. However, if you, instead of doing this, right, because in this case, you were actually able to get the bases the same. But let's say I didn't get them the same, or I couldn't. What I would do is bring this x to the front, right? Because the inverse operation of an exponent is a logarithm. So I'm going to get x log 2 is equal to log 8. And now I'm going to get x is equal to log 8 divided by log 2. And that value, when it's all said and done, and I plug that into my calculator, is going to be 3. Just please keep in mind, you cannot cancel your logs. You cannot cancel 8 with 2. This is actually a quantity divided by a quantity, and you can never break into those quantities. They're separate. For this problem right here, we don't know what this equals also. So we're going to go 9 to the x power is equal to 3. And remember, that's actually 3 to the 1 power. So is there a way to get the bases the same? That's the question that you would be asking yourself. And that would be yes, the 9 actually can be rewritten as 3 squared. But remember, there is an x out already there. So that's going to be 2x. So 3 to the 2x is equal to 3 to the 1 power. And if my bases are the same, then I can set my exponents equal to each other. So 2x equals 1 and x equals 1/2. So that would be my answer to this problem. Just showing you a different way of doing that. Again, base to across the equal sign. So you'd have 9 to the x power is equal to 3. I know I can get my bases the same. I already did that here, but I am going to show you this by logging and bringing this outside the x out of the exponential place. I'm taking the inverse, which is now going to be x log 9 is equal to log 3. So x is equal to log 3 divided by log 9. And when I solve that, I'm actually going to get, with my calculator, 0.5. And of course, 0.5 is 1/2. And that's what I did want to get because that was the solution. Couple of things that I do want to mention that I do have on here. And like this right here, log base a of 1 equals 0. A to the 0 power is 1. True. Also, this is what we also talked about when we had log base a of a. Well, that's always going to equal 1. If these two values here are the same, if my base and my argument are the same, then my answer is equal to 1. So these problems right here are just some practice problems that I'd like you to do. And these are not solving anything. It's actually just saying rewrite it. So that's this way is actually pretty easy. You're going base to across the equal sign. So 6 to the 2nd power is equal to 36. Verifying that, I could do that 2 ways. I could say, well, 6 squared is 36, and that equals 36. Or I can say 6 squared is equal to 36, which is 6 squared. So yes, those are the same. When they say rewrite it into an exponential form, this is all that they're actually asking me to do right here. Okay. This one right here, base to across the equal sign. So that's going to be 289 to the 1/2 power is equal to 17. And they're just asking you to rewrite that. And we just did. So you're done. Keep in mind that, and I just want to talk about what that is saying. 289 to the 1/2 power. Half power is actually a square root. So it's actually saying 289 to the 1 power with the square root inside here. And the square root of 289 is 17. So that is a verified. This is the part that a lot of people do have some problems with, and that is taking the exponential equation and just rewriting it. We're not solving it. We're not simplifying. We're not verifying. We're just rewriting it into a logarithmic form, which is basically this. So they want that. And so you're going to see log. And so what's my base? My base is actually the same base as that. So if that says 64, that's 64. So base to across the equal sign, remember, this would have to be a 1/2 over here. And my argument became, or my answer became my argument. So that would be my, just rewriting that. For this problem, again, the base becomes my base. So that's going to be log base 12, base to across the equal sign. So my answer becomes my argument. So that's 144, and that's equal to 2. Rewrite each equation in log form, in logarithmic form for these two problems right here. So I would bring this out front. So I have negative 14 log, I'm not sure that's not actually what they want. I was going to say negative 14 log u equals log v. Let me just show you what that looks like. And then in that case, what am I solving for? So they're not asking me to solve for anything because actually I have 2 variables and that's not going to work. All they want you to do is to rewrite it. So you're going to say log base is my base. So u down here, my argument is my answer. So this would be v is equal to negative 14. For this problem, rewriting that, it becomes log base 8 of a is equal to b. Remember, your answer becomes your argument, and your base, which is 8, becomes your base here. For these problems, they're asking me to evaluate, which is basically solve in this case, because I'm going to set each of these equal to x. So this is going to be 4 to the x power equals 64. So I'm going to try to get the bases the same. Now, I actually have a choice on this. See this 4 squared? So I can do this. I can say, well, that's 4 to the x power equals 4. So think of 64. 64 is 4 times 4 is 16. 16 times 4 is 64. So that's 4 to the third power. Okay. And if my bases are the same, I can set my exponents equal to each other. So I have x is equal to 3. Now, a lot of people will try to reduce their variables to as small as they can. So when I start off, 4 to the x power equals 64. So from here, I can actually, I'm gonna go over here and show you another way to do that. 4 can be written as 2 squared, but there's an x up there. So you would say 2 to the 2x equals, and 64, if I broke down 64, there's actually 6 of those, so 2 to the 6th power. So if my bases are the same, I can set my exponents equal to each other, so 2x equals 6, and then divide by 2, and I get x equals 3. So I'm going to get the same answer. I just did that 2 different ways. There's no equal sign, so I'm actually going to set that equal to x. So I'm going to go 6 to the x power equals 216. I could do this a couple ways. 216 divided by 6. Let's see. 216 divided by 6. It does go in there. So let's see. What does that equal? Okay, 36. And so what that means is this is, let's see here, 6 to the x power equals 6 to the third power. So x equals 3. I do want to say that what I could do is just, if I didn't have a calculator, or actually I would need a calculator, but another way I could do that, I remember, is to bring that x to the front. And I could say x log 6 is equal to log 216. And so x would be equal to log 216 divided by log 6, and I'd still get x equals 3, but it's just another way to do it. This one, I'm going to set this equal to x. So I'm going to get 4 to the x power equals 16. And that's 4 to the x power equals 4 squared. So x is equal to 2. Again, I could have broken that down farther and said 4 is actually 2 squared to the x equals, and 16 is 2 to the 4th power. So I get 2x equals 4, and then x is equal to 2. So again, I know I'm doing this twice and I'm spending a lot more time than I need to on this, but I do want to show you that there are options to these problems, and you don't just have one way to do it. So this was going to be 5 to the x power is equal to 125. I'm going to try to get the bases the same. So I have 5 to the x power equals 5 times 5 times 5, which is 5 to the third. So I have x equals 3. This one right here is a little bit tricky, because once I set that to equal to x, I'm going to go base to across the equal sign. So 3 to the x power equals 1 over 243. And so 243, 3 goes into that, or divides into it. So meaning here's 3, here's 243. 3 divides into 24, 8. 3 divides into 3 once. So 3 times 81. But 81 breaks down to 9 times 9, which is 2 and then 2. So I actually have 4 threes here from the 81 plus another one. So that's 5. So what I really have is 3 to the x power equals 1 over 3 to the 5th power. And remember, when I change the base from the denominator to the numerator, I get 3 to the x power is equal to 3 to the negative 5 power. So I have x is equal to negative 5. Okay. For this one, set it equal to x. And I'm going to go 2 to the x power is equal to 4. In this case, pretty simple. I can just say 2 to the x power equals 2 squared. And then therefore x equals 2. And that's the answer to this problem right here. Last two problems, remember these two, if the base is the same as the base here, my answer is 144. And likewise, 5 log base 5 of 17 is just 17. So what if the base isn't common? How would you calculate on a calculator? We've been talking about this as a change of base formula. So basically what happens here is log base b of m is equal to this value here. So if you have log base b of m, that's the same thing as saying log base a of m, so some log value, divided by log base a of b. And what that means is we're going to use this right here. We're going to say log base 5 of 8 is equal to x. So we're going to go 5 to the x power is equal to base to cross equal sign is equal to 8. I want you to notice that for this problem, you actually don't have the same bases. So how do you solve it? So that's what this example here is showing you, that you're going to bring this out front, and that's going to be x log 5 equals log 8, x equals log 8 divided by log 5. And watch how, see this denominator here, this 5 became my base value. My argument became the top, okay? So for example, if I said log base 6 of 3 is equal to x, how would I rewrite that as a change of base formula? So you actually can just write that x equals log base 10 of 3 over log base 10. Or not, you don't have to write base 10, but there's the 10 there, of 6. And so you could just rewrite that. Now, most of the time they're going to ask you to solve that. And so for solving that, in order to solve that, you would, divide whatever log base 3 is. Okay, so hold on a second. So log base 10 of 3. So that's going to be, the lights just went out in here, so can't see. 3 divided by log base 10 of 6, and that's about 0.7879. So it's about, so x is about 0.78795. Okay. Okay, so we also have something called a natural logarithm. And what I do want to talk to you about is on your calculator, under these buttons right here, these right here, you're going to notice that above the x, so if you were to look at your calculator and find the, let's say, x squared button, above that, you would see a square root. That's an inverse. Above the 10 to the x power, you'd find a logarithm. See the log button is, most people, it's like in blue, it's a rewritten part. And then it's like the lighter color. You'd have to, most of the time you have to push control in order to get to the second or the shift. Anyway, the ln is our natural log, and logarithms base e are called natural logs. Now, in previous lessons, we've actually talked about the value of e, or e to the 1 power, and that is about 2.718. What we've done is we've actually graphed this before, and we've graphed, let's say, 2 to the x power, and we've graphed like e to the x power, and basically you have your 2 to the x power that looks like that. And then you've got your 2 to the e, sorry, these are got to go through the same value, so let me fix that. And so 2 to the e power, or excuse me, e to the x power would be the same kind of thing, but it would actually be a little bit, and they both have to go through 1, but it would be a little bit steeper because it is 2.7 as opposed to 2 to the x. So in these problems, let me erase that because that's not ln of x. In these problems right here, what they want you to know is that ln, being the natural log, is the same thing as log base e of x. So this is kind of important. So you do need to rewrite. I mean, I would put that in my notes. Ln of 53, for example, means log base e of 53. meaning I can replace this part right here, log base e, and replace that with ln of 53. Similarly, if ln of 53 is equal to 3.9, then e to the 3.9 power is equal to 53. So in these problems, these problems are just basically meant to practice and typing these in your calculator. So you should take some time and make sure that you can type these in your calculator. Some of these might throw you off a little bit. So ln of 500,000 is 13.12. ln of 0.0000123 is negative 11.3. Now, this one may or may not surprise you. In one of the problems that we did earlier, we had something like log base 5 of negative 10, or I don't remember the number, negative 18 is equal to x. This is not possible. You can't take a log of a negative. Oh, what is going on there? You cannot take a log of a negative argument. So what ends up happening here is that for this problem, it doesn't work. So you end up getting it undefined. Now, ln of e is 1. And the reason for that, and remember, we were talking about, this is a little bit tricky right now. Oh, I see. And the reason for that was that ln, remember, we can replace ln, and we can replace ln with log base e. Now, if I have see, just this, replacing ln is log base e. So if I have log base e of e, remember, if this base was lower, if that's a little bit, okay, let me fix it. Let me rewrite that. If I replaced ln with log base e, and then I have my value here. Remember, if these two values are the same, my answer is 1. And then, of course, ln of 1 is 0, because same thing, log base e of 1 is equal to, we don't know, you're going to say, well, anything to that power is got to be 0. Okay. The other thing I wanted to talk to you about is this graph, which I don't know if you can see right now, but it does say f of x is equal to ln of x. And what we did talk about as a logarithm here, e to the 2.7, well, that's going to be the inverse of ln. So if I were to graph e to the x power, and it would look something like this, well, ln of x is going to be an inverse of that. So it is going to go through here. So what would that look like? And that's going to be, how would I graph this? This would be like this, right? Okay. And so that would be its inverse. And so you actually don't have to know anything or how to graph an ln of x other than that it is an inverse of e to the x power. And so you can just reflect it across your y equals x axis, which is this axis right here, y equals x. These are just some conversions that I'd like you to do. This first one, and then I would turn off the video or pause it and then start it again just for you to go through and practice these and then check your answers. And so they want these to be log equations. So they want them in a log form. So we would say, first of all, to get this base here, I would say, well, that's log base e of, so based across the equal sign of 70 is equal to a. Now keep in mind, log base e is ln. So another way of writing that would be ln of 70 is equal to a. And of course, I can actually go on to my calculator and find out what ln of 70 is. This one right here would be log base a of q is equal, that's very strange. Having some problems with this. So let me erase all this stuff here. So what did I do here? This was log base e of 70 is equal to a. For this problem, we had log base A of Q is equal to 8. For this one, we would have log base 2 of 32 is equal to X. For this one, we would have log base E of 7.3891 is equal to 2. And for this one, I would actually take the log base E and change it to ln of 7.3891 is equal to 2. And that one is just, there's no X in this problem. So if there's no X or variable, you're only verifying that. For this problem right here, again, there's no X, so we're just verifying that. That's 5 to the negative third power is equal to 1 over 5 to the third power. And when I bring this up to the numerator, I get 5 to the negative third power does in fact equal 5 to the negative third power. For this one, convert to exponential form. So we're going to go base to across the equal sign. So 4 to the t power is equal to 7. And that's it. They didn't ask us to solve it. I could solve it. If I solved it, I would pull that out front. T log 4 is equal to log 7. And I get t is equal to log 7 divided by log 4. And then I would get an approximate answer, whatever. You would just use your calculator and divide log 7 divided by log 4. But they didn't ask us to solve it. They just said convert it to an exponential equation, which we did. And also the reason why I didn't get the same base and do that, set the bases equal to each other so the exponents would be equal to each other. The reason why I didn't do that is because I'm not going to get the bases equal to each other because one's 4 and one's 7 and they're not going to equal. For this one, we're going to go x to the 1 power is equal to 5. X equals 5. That's it for that problem. This one would be r to the k power is equal to q. And again, they're not asking me to solve anything. They're just asking me to convert it to exponential form. So a couple types of special logarithms, again, and this is just doing some sort of like a little review. This says log base 10 of x. Well, see the base, there's no value here. We know there's a 10 there, but assuming that if it's not there, we know it's a 10. So these are equal to each other. ln of x means log base e of x. And so here's just some special relationships that are really important that you ought to know. Log base b of x equals y. Remember, it's going to go base to across the equal sign. So b to the y power equals x. Logarithms are really exponents or powers. Log base b of b. So remember, these are both the same. That's it. Your answer is going to be 1. Anytime you go log base b of 1, that's going to be 0. Log base b of a is undefined if a is negative. Remember, if I were to have a negative argument, like -5, my solution is no solution. There is no solution for this problem. Also, you cannot have an argument that's 0. So if your argument is 0, your answer is undefined also. And lastly, when your bases are the same, again, this is basically the same. If my base and my argument are the same value, it's whatever that exponent is. So it's just going to, in this case, the answer is n, because you would go base to across the equal sign, b to the n power is equal to b to the n power. Bases are the same, so the exponents are equal to each other. I think, a couple of estimate and then find the exact, we've already actually done this slide, so that's a copy of that. So that's an introduction to logarithms, and I hope that that's helped you, and I'll see you next time. Thank you.